I just realized my mic was on. You guys can hear me breathing. How about that? I'm gonna go ahead and hop off the mic so I can breathe in peace. You guys listening? Let me know. Let me know in chat if you've got some questions for me. We'll get started here in about 8 minutes, 7 minutes, 7 minutes. What's up, guys? We'll get started in 1 minute. Got to update the text. Give me 1 minute. All right, peeps, what's happening? Free GMAT prep hour, the September 23rd, 2020 edition. I have not done one of these since February, and boy, has the world changed since then. Go ahead and open up the chat box and say hi, so I know that you've got access to this. I'll be asking you guys to give me some responses in there. All right, hey Ashley, how are you? Kim, Vishru, Jenny, awesome. Thanks for coming. Oh, we got a good number of people here. Yeah, we do these every couple of weeks in general. So I don't know when the next one is. I know I'm doing one sometime in October. I have not figured out what topic to teach. If you have any ideas, this is what the chat box is for. I do know what we're doing today. I'll keep you in suspense for another minute here. Although if you're watching this on YouTube, it's probably in the title, so spoiler alert. Cool. Before we get started, October 6th is the next one. Good to know. Am I doing that one? I feel like I should know these things. No, I'm doing one on the 18th. I'm doing one 2 weeks after that. Reed. All right, Reed does a good job here too. So y'all should book October 6th and go see Reed's talk. That'll be the next one. He does a great job on these. Cool, just want to remind you guys, in addition to free GMAT prep hours, you have some additional free options here. Of course, come check out and show up to one of our session ones. Yeah, our full course is 9 sessions long, and we invite you to the first session. Just sign up for a trial class, find a session 1 that matches your schedule, and then it's up to you to see if it's something you want to continue. If not, good luck. We also offer a kind of a shorter version of our Interact course, which is a more of a self-study course that has homework assignments for you to do in between lessons, a bunch of video lessons, and you can kind of preview that as well. So go check those things out. All right, what we're doing today. What we're doing today is we're going to talk a little bit about probability. This is a topic area I get a lot of questions about from my students, private students, tutoring students, course students. And I will go ahead and just give you a disclaimer here. Like, I think probability questions overall can get pretty tough. And so as with like any type of question on the GMAT, we have to be ready to not overcommit our time and our energy and our mental capacity into these tough problems. So what I'll say is you should feel okay bailing on the tough probability questions, just as you could bail on the tough geometry questions or tough any questions, and not feel guilty about it, right? There's no shame in getting like really difficult problems wrong on this exam, unless it takes you like way too long to get the problem wrong. So again, you should feel okay just bailing on these questions if they completely flummox you, but I do want to make sure that we leave today with a solid like framework for understanding how to maybe tackle some of the more manageable problems, because we definitely don't want to like swing and miss on a relatively easy probability question. So we're going to go ahead and start by building up from the basics, and then I'll have a set of questions for you, and some of the questions are kind of challenging. We'll talk about how to do them, and then we'll see if there are questions throughout, questions at the end. If we have extra time, there might be a bonus question. And if there's extra time, I'm also ready to just kind of take all the questions you want to fire away at me related to the GMAT. So let's go ahead and dive into a little bit of probability stuff. I'll give you a little warm-up question here. So if you have answers, you're welcome to just send them into chat. If you don't want to like spill the beans on all these problems, just send them into the panelists. Don't send them into like absolutely everybody sitting in the audience. Don't want to like ruin the surprise. On this one though, I mean, I'm getting a lot of answers in chat already, and they all look pretty good. I imagine this is a question that you might be able to get correct without even like thinking like how you're doing it. It's just like the answer just kind of immediately pops up. Yeah, if you've given me an answer in chat, that is correct. So what we want to do is often, like when we deal with really hard questions, is to, you know, look at an easier version of the problem and build it up. And we can do that with probability. Like the hardest probability questions can be seen as like lots of easier questions put together. Okay, so a standard six-sided die, what is that? I have some here. Those are these guys. I mean, I don't know if you know what they're called. Plural are dice. A singular one is called a die. And we roll one, and we want to know what's the probability that we're going to roll a 4. Well, to figure out probability, we just need to remember like this equation. All right, and this is how it's often kind of described in text. Probability is determined as the quotient, right, or the resulting fraction of the number of desired outcomes over the number of total outcomes. Now, desired outcome, like desired is, it might not necessarily be like what you really want. Like let's say you're playing a game and like if you roll a 4, you're going to lose. Like in that case, we don't desire a 4. So don't think of desire as like what you want, but it's like in the problem, what the specific result that you're searching for divided by all the possible results. And of course, in a six-sided die, there's only one side that has a 4. There is one desired outcome, one way to roll a 4. There are 6 total options. And so the probability here is indeed 1 out of 6. Okay, and you can see that like this is a fair die. There's a 1, there's a 2, a 3, a 4, a 5, and a 6. And so if I roll this thing 1 out of 6 times on average, I'm going to get a 4. Okay, so that probably makes like pretty intuitive sense. But we have to understand this fraction in order to really move on to harder and harder concepts. So let's try another problem. Problem 2. Take a moment, hit me up in chat when you got it. And again, like I think for a lot of you, this might seem obvious as long as you know what your prime numbers are. So like this is how they can make a basic probability problem just like a little bit harder, is like now they're actually quizzing you on like what the low prime numbers are. Okay, and so we'd have to know here that actually 1 is not a prime number, right? Technically 1 is not a prime number, and that is something you need to know. I do think it's worth knowing your first, you know, the first 10 primes for sure. Come back here, 23. And so the only ones that would be on a on a six-sided die would be these ones. So we're going to go through our same fraction here, our same equation, and say, well, the number of outcomes that fit the description, a prime number, there's three of them. I could roll a 2, I could roll a 3, I could roll a 5, and there's still 6 total rolls possible, right? 1, 2, 3, 4, 5, and 6. So again, 3 ways to roll a prime out of the 6 total options, and that gives you a probability of 3 out of 6 or a half. Okay. So yeah, if you said 4 out of 6 or something like that, like it's probably because you thought 1 was a prime number, and that's just something we just need to know. 1 is not a prime number. A prime number is an integer that has exactly 2 factors, and 1 has 1 factor. Cool. All right, we've done a little warm up. I want you to keep this equation in mind as we do the next problem. The next problem is a little bit tougher, all right? We're still gonna be playing dice games, but it's gonna be a little bit tougher. Give you some time to think through this. That's been 1 minute. I'll give you 1 more minute here. Another 15 seconds here. All right, that's been about 2 minutes. So obviously this is not like a normal GMAT problem because there's no answer choices. And GMAT problems are always multiple choice, data sufficiency or problem solving. So you'd have like a little more to go off of than no answer choices. Like you might be able to estimate, like, would this be common? Would this be rare? Like imagine rolling 3 dice. Like what would be like a normal sum? Like a really high sum would be 18. If you roll like all 6s, right, you get 18. The lowest sum possible would be 3. And it's kind of like a bell-shaped curve between 3 on the low end and 18 on the high end. And so like the most common rolls with 3 dice would be like 9, 10, 11, 12, because of like the average of like 3s and 4s. But 5 is like on the very low end. All right, and so it's going to be hard to roll a sum of 5. Like if one of the dice is a 4, you already can't roll a sum of 5, right? It's like you're guaranteed to have at least 6. So it's going to be pretty tough to roll a 5 or less. All right, so we still want to tackle this problem, I think, thinking of it this way. Like, how many total ways are there to roll 3 dice? And you could like try counting 1, 1, 1, 1, 1, 2, 1, 1, 3. Somebody stop me. That's going to take forever. But there's an easier way to figure out like the number of total outcomes. And then we'll want to think of like, hey, which of those would sum to 5, okay? So let's go ahead and think about the denominator here. What's the total number of outcomes that you could get rolling die 1, rolling die 2, and rolling die 3? We've got like a 3-digit number, right, for our roll combination. Sid, that looks good to me. Mm-hmm. What do you think, guys? How many ways are there to roll like a 3-dice combo? Cool, Melissa, that looks good. Jadip, that looks good. Gina, that looks good. Yeah, not 18 though, not 18. And not 6 factorial, and not 3 to the 6. We're getting close. It's gonna be 6 to the 3rd, okay? 6 to the 3rd. And we wanna think about that, like I've done one of these videos like a couple years ago now. I probably had longer hair, less gray too, where we can figure out like how many options there are for things. There's like this is a probability lesson. I did a combinatorics lesson a while ago. And it's like, look, with dice 1, you have like options 1 through 6. So there's 6 options here. There's 6 things dice 2 could be, and there's 6 things dice 3 could be. And what we say is when we say and, we multiply. Okay, and so you could write these all out. You could say, oh, 1, 1, 1's an option, 1, 1, 2, 1, 1, 3, 1, 1, 4, 1, 1, 5, 1, 1, 6. Those are 6 options already that start with 1 and 1, right? So that tells you like, look, there's 6 options for the 3rd die. There would be 6 options for the 2nd die. There would be 6 options for the 1st die. I can't write all this out because 6 to the 3rd is 216, and I would fill up the whole screen. I would take up the hour, and then you'd have learned nothing, okay? But there are 6 to the 3rd total ways to roll 3 dice. How many of those sum to 5? I think it's worth just trying to list these out. Okay, like of those 3-digit combinations I started writing out, like did any of them add to 5? Yeah, one of them did. 1, 1, 3 added to 5. Awesome. Let's try to think about like what other ways we could add up to 5. You might be able to get creative right here. You could just mix these up. Say, well, if the 2nd dice were 3 and the 1st dice were 1 and the 3rd die were 1, right? If I just switch these, this would also add to 5. And so we can kind of just go through these rotations, right? So here are 3 ways you could do it. And I'm getting a bunch of answers in chat. Here are the other ways. And that's it. Those are the only ways you can roll a sum of 5. Right. Again, they have to be like small rolls because again, like once you roll a 4, the least you could roll on 3 dice would be 6, 4, 1, 1. Okay. And so there's 6 ways here, 6 desired outcomes out of 6 to the 3rd total ways. And so that leaves 1 out of 36. Yes, cancel out a factor of 6, 1 out of 36. Yeah, all 3 dice are identical, but when you're listing out the 6 times 6 times 6 rolls, you're actually like counting all the different rotations of the same 3 combinations. So if you rolled like 3, 4, 1, we're counting that as different than 1, 3, 4 and 4, 3, 1 and all the other rotations in these 6 by 6 by 6s. So think of it as like die 1 as die 2. Nope, come back. Die 2 and die 3. And we want to like be specific here of all the ways you could roll for die 1, die 2, die 3, because we're being specific here. And so if we're specific about the order here, then we need to be specific about the order here. So you just have to be consistent both ways. All right, so that'll be 1 out of 36. All right, so that's probably about as tough as they could make like a basic counting probability question with dice. But here, like, it seems like there's gonna be so many different ways to roll a 5, but there ends up really not being that many ways to do it. Cool, same principle though, desired outcomes over total outcomes. Let's try another problem. Only 2 dice this time. I'll give you about 90 seconds to think about it. Larry, that was so fast. How'd you get that? All right, I'm just going to tell you that still no one has given me the correct answer yet. It's been 60 seconds. I'll give you another 30 seconds or so to think here. I'll let you know when the first correct answer comes in chat. I still haven't gotten it yet. All right, just got it. I got it from 2 people. I got it from Nick and JL. I got it from Sato as well. All right. All right, so I'm going to use this problem to introduce like a few concepts here. Okay. Let's first think about like how we could get an even product, right? Like, what are the ways that we could get an even product? And I'm not thinking of like, well, you could roll a 2 and a 5, like that's one way, and you could roll a 3 and a 6, like that's another way. Sarah's given me a good one. She's given me a couple options, right? She's like, you could roll an even number and an even number, or an even number and an odd number, or an odd number and an even number. Yeah, so we want to think like, okay, how are the ways, like what would the ways look like that get us to an even product? And we'll kind of think about it with like the first die and the second die. Okay, the first die could be even. And the second die could be odd, because even times odd, right, we're finding product. Even times odd is even. But you could do it another way too, right? You could switch these and say, well, what if the first die were odd and the second die were even? That multiplication still gets me to an even product. Those are not the only ways to do it. If they are both even, right? If you roll a 4 and a 2, well, that product is 8. And so that still counts. We want to count that. Like there's a chance you roll 2 dice, one's a 4 and one's a 2. Okay, you want to count those. All right. And so there's a couple interesting things happening here. Okay. There's a couple like avenues that get you to an even product. You could roll even and odd, or you could roll odd and then even, or you could roll even and even. And what we want to think about here is how the ands and the ors work. Okay. Whenever you see and in a, Sid, that's a good way to do it. We're going to do it in a moment. Whenever you see and in a probability question, like I need this to happen and I need this to happen, right? Like this happens a lot, like at the end of sporting seasons, and like one team is trying to like get into the postseason. And it's like, well, team A needs team A is trying to get into the next round of the season. It's like, well, team A needs to win their game, and they need team B to lose, and they need team C to win by at least 8. Like if you need all of those things to happen, the chances of it happening get less and less with each like additional criterion that needs to happen. Okay, so when we see and, what we want to do is we're going to multiply the individual probabilities. Okay, so that you're multiplying fractions by fractions, and the resulting probability, the total probability, gets smaller and smaller. But in this case, we also have the word or, and so it's like, oh, that's not the only way that this could happen. All right, there's another way we can get this done. And when we're allowing for additional ways to get things done, we are opening up, we are adding likelihood to the probability of something happening. Like, oh, team A could win, or team B could lose, or team C could lose by 8 points, right? And it's like, if I only need one of those three things to happen, I have a better chance if I'm on team A that I'm going to get to my goal. All right, so what we want to do here is remember that whenever you see and, we're going to multiply probabilities. And whenever you see or, you're going to add probabilities. So let's tackle this line by line, row by row here, all right? What's the probability that the first die is even? Well, think back, there's 6 possible numbers you could roll with the first die. 3 of them, 2, 4, 6, are even. So there's a 1/2 chance that the first die is even. And similarly, there's a 1/2 chance that the second die is odd. So what's the probability that the first die is even and the second die is odd? It's 1/2 times 1/2, which is 1/4. Okay, well, what's the probability that the first die is odd and the second die is even? Well, it's still going to be 1/2 times 1/2. And so the probability of this sequence happening is also 1/4. Okay, what's the probability that they're both even? Well, there's a 1/2 chance, 50% chance that the first roll is even and a 50% chance that the second roll is even. We multiply 50% by 50% or 1/2 times 1/2 again and get another 1/4. Okay. And so what we now want to do is say, well, there's a 25% chance that it happens this way. There's a 25% chance that it happens this way. And there's a 25% chance that it happens this way. And so we're going to add all those up. If any of those happen, I'm going to get an even product. We add these up and we say, the overall probability that I can get, yeah, you said it, that we can get to even is 3 out of 4. It's going to happen more times than not. And if you wanted to, you could list out all the possibilities, right? There's 6 options for the first die. There's 6 options for the second die, which means there's 36 total combinations. And 27 of those 36 will be even if you multiply them. Okay, so that's one way to do it. But there's another way, yes, there's another way that both Sid and Sato have given me. Why is it not? Hold on, I'm trying to read it, something in chat. It doesn't matter if the first or second is even, because both of them give you an even product, regardless of, like, as long as there's an even number somewhere in here, the product will be even, because any integer times an even number is an even product. It doesn't matter which one is even. Let me see if I can come back to this. I'm getting a handful of questions, and I don't know if I can get to them all right now, but we'll try to circle back around in a little bit. Okay, the other way to do this is to think about the opposite problem. So, okay, so the question came is like, we did even and odd, and we did odd and even. So we kind of like did the mirror images of them. Why didn't we do the mirror image of even and even? Well, the mirror image of even and even is itself, right? So we don't want to like double count those. Yeah. Trying to think if there's like a corresponding, like an analogy I could use here. I'm not sure I can come up with an analogy. It's like if we are flipping, other way you could do it, the same problem is we're flipping coins, right? We're flipping coins and we're flipping heads and tails. You could have heads and tails, tails and heads, and tails and tails. These are like the 4 ways to do it, right? So basically this question would be similar to like, what's the probability you flip at least 1 heads? And here it is, it's 3 out of 4 ways you flip at least 1 heads. We don't want to double count this. We don't want to say, oh, heads and heads could have been heads and heads, because it's the exact same thing. So we don't want to count it twice. And that's why we're not flipping even and even. Cool. All right, so the other way to do this is to think about the opposite problem. And so what we need to remember here is in any given scenario, all possible probabilities need to sum to 1, to 100%, okay? Right? And so this knowledge allows us potentially to solve for the opposite probability, okay? So if you roll 2 dice, the product of those 2 rolls is either even or it's odd, okay? And so we know that the probability of getting an even product plus the probability of an odd product is 1, because like these are your 2 options and they have to sum to the entire 100% of options. So if we're going to solve for the probability of an even product, one move we could do is rearrange this equation and say, oh, the probability of getting an even product is just 1 minus the probability of getting an odd product, and go hunt for the probability of an odd product, because that might be easier. Because what is it going to take to roll an odd product? Well, the first die and the second die both have to be odd. And that's the only way to do it. There's not like an or option. It's not like you could roll odd and odd or odd and even, because odd and even won't give you a product that's odd. So this is it. And this is why the 1 minus technique might be faster, because instead of summing up 3 component probabilities, you solve for this 1 probability and subtract it from the total. So the probability of rolling an odd first die times the probability of rolling an odd second die, half times a half, which is a quarter. That's the probability of an odd product. And so 1 minus the 1/4 is 3/4, which is what we got on the previous screen. So a couple ways to get to the same answer. And like, which one's better? I don't know. Like, I would probably do the 1 minus technique, but that's going to be, I don't know. It's a personal preference. Okay. Cool. All right, let me see if there's any other questions here before we go look at the problem set. All right, no questions are coming in. Awesome. You guys have been great so far. Let's go take a look at the set. I've got 3 problems here. I'm going to go ahead and give you 6 minutes to think about them. The first one is from the official starter kit that you get on MBA.com. So you might recognize it if you've done a bunch of those problems or practice exams. The second question and the third question, which are numbered 6 and 7, because we've already done 4 today. These ones I just made up. All right, so I'm going to go ahead and put 6 minutes on the clock, give you some time to wrestle with these, and we'll circle back and talk through them. If you have answers, let me know in chat, and I'll give you some feedback. That's been 2 minutes. You got 4 minutes left. That's been 4 minutes. You have 2 minutes left. Got 15 seconds left. All right, that's 6 minutes. These are hard, guys. I think I always maybe bite off a little more than I could chew. I put some I always make up my own problems for these things, and I get some that are just like really brutal. But someone got them all right in in chat. That's awesome. So I mean, what's the probability that if you guessed on all of these, you'd get them all right? So you could do that too. It's 1 out of 125, by the way. All right. So again, I think this kind of underscores the idea that like it is okay to bail on some of these questions. Okay, it's okay to bail on some of these questions, and you shouldn't feel guilty about doing so. We're going to get problems wrong on this exam. We want to make sure that the problems we're getting wrong are the ones that we deserve to get wrong, like these really ridiculously hard problems, and that we're not over-investing our time and energy in these types of problems and then not having enough time to get the problems that like we ultimately should be able to do. Okay, because now we're missing the hard ones and the easy ones. If you have your choice of missing problems, just miss the hard ones, right? The hard ones affect your score the least, right? So, okay, let's dive in here. Oh, this is wrong. This is not Manhattan Prep. This is I forgot to change the. I don't want to get in trouble. I don't know who watches these videos. Official GMAT starter kit. There we go. Credit is given. Cool. We're going to pick two of these four expressions and we're going to multiply them. And we're going to see if they give us this form, which, ooh, by the way, a nice little difference of squares form here, hidden with this weird b thing. But yeah, it's something squared, where b is an integer. Okay, let's go ahead and label these terms. I'm going to label this term A. I'm going to label this term B, this term C, and what could I label the last term? No, it's going to label D. All right. Which terms can we pick so that the product is in this form? Let me know in chat. What terms can we pick? Like let's take a look at some of these. Like B and D. Like if I multiply x plus 5y by 5x minus y, right? And we FOIL this. Like, what are we going to get? This is going to be a little messy. The first term gives me 5x squared, and already like I'm a little suspicious, right? I need x squared, not 5x squared. The outer term gives me minus xy. The inner term gives me plus 25xy. And now the last term gives me minus 5y squared. I can't get this into this form. And maybe like trying one of these kind of lets us see like, oh, I don't think this is going, like some of these are going to work. Right? Like B and C won't work. Right? They're going to give you some strange inner terms. And you want the inner terms to cancel, right? There are no outer inner terms here, right? This is going to give me like plus 24xy. Like that doesn't fit anywhere here. I guess that's why they say B has to be an integer, because maybe B is some like really weird square root like of this. That's also like an imaginary number. I don't know how that would work. So the only way that we can do this is pick terms A and C. That's it. Okay. We can pick terms A and C, and we have some options, right? Like we could pick A first and then C, or we could pick C first and then A, right? If we're going to pick them at random, like if you're going to play the order game here, then you could do either of these things. And the key here is to remember, you could do this or this. So let's try to calculate the probability of picking term A and then picking term C. Okay, so we've got these four terms to pick from. They're putting a a metaphorical hat, and we grab one. What is the chance that it's term A? Well, 1 out of 4. Right? There's a 1 out of 4 chance that the first term you randomly picked is term A. Once you pick term A, you also have to pick term C. So I need to pick term A, and then I need to pick term C. If A is out of the picture, there's a 1 in 3 chance I pick term C. And so there's a 1/12 chance I pick A and then C. All right. The other way we could have gotten terms A and C is if we had actually picked term C first. That's a possibility, right? And then we picked term A. Guys, I'm doing the or because these are two distinct ways to do it. You could first pick term A and then pick term C. You could also pick term C and then term A. You're correct that the pair of A and C, it doesn't matter which way you multiply it. Well, I'll try to show that later, okay? But if you're kind of going through and thinking about these as like single events, then the order does matter, okay? There's multiple ways to get the right answer here, and I'll try to walk through that, and then you can kind of maybe see where the order does matter and where it doesn't matter, okay? So if we need to pick term C first, we have a 1/4 probability of that happening. And then what would have to happen is you'd have to pick term A, right? That's the only one left of A, B, and D that'll give you this form. And so the probability of both of these things happening is also a 12th. Now, because these are two separate possibilities that could happen, right? You could choose A, then C, or you could choose C, then A. Because those are two distinct pathways through the terms, you're going to add these and get 1/6. And that is the probability that this is going to happen, okay? Let me show you another way you could think about this. If you know you have to end up, why is the second term 1/3? Could you not pick? No, you can't pick the same one twice, because once you've picked term A, like you can't repick term A, right? 2 of the 4 expressions are chosen. So if you picked A and A, you've only chosen one of the expressions. So once you choose term A, like it's out of the running for the second term. Yeah. It's basically you choose these without replacement is sometimes how it's called. Once you choose A, you don't get to put it back. In the marble question, the third question in the set, question 7 overall, that one did have replacement. Yeah, also, yeah, and A doesn't give the form, C and C doesn't give the form, but you couldn't pick A and A because then you wouldn't have picked 2 of the 4 expressions. So the other way that you could think about this, and maybe there's a couple more ways, but if you have to get, must end up with A and C somehow, right? Go ahead and put these terms back here. And now they're going to be lowercase because I'm just inconsistent. If you have to end up with A and C, but it doesn't really matter the order, like what you have to do from the outset is pick one of those terms with your first pick, all right? So what's the chance that with your first pick, you get A or C? And I'm saying it, A or C, right? The chance that you get A or C is a half. And then the chance that you pick the other one, right? Like if you picked A, what's the chance that you pick C next? Or if you picked C, what's the chance that you pick A next? So you have a 1/2 chance of picking either A or C first. And then the chance that you pick the one that remains is a 1/3. All right. You need to do both of these. You have to pick A or C first, and then you have to pick the other one second. So you have a 1/2 chance of not hitting one of the bombs, B or D first. And then you have a 1/3 chance of avoiding B and D again with your second pick. A 1/2 times a 1/3 is still a 1/6. The other way you could do this is just list out all the ways that you could pick these, okay? And this is where I think some of the questions about duplication are coming in, okay? But here are all the ways that you can pick 2 letters. I'll just list them alphabetically. AB, AC, AD. Those are the 3 ways that start with A. BA, BC, and BD. Those are the 3 ways that start with B. Now you're probably already noticing there's some repetition here. CA, CB, CD, DA, DB, DC. These are the 12 possible ways to do it, okay? Here's one way that will succeed at giving you this form. And here's the other one. That's 2 out of 12, which is 1/6. And so here's where like you're saying, oh, there's duplication. Yes, there is duplication. In this case, AC and CA, they're the same two letters switched around. But again, if the order matters, like then if the order matters in how you're selecting, the order matters throughout. Like we have to be kind of consistent here. If you only wanted to list pairs that don't rearrange into themselves, the only options are these. And again, just 1 out of 6 of those is what we're looking for. So again, the question is, how do you know the order doesn't matter? You can choose for it to matter or for it not to matter. If you choose for it not to matter, that's fine. Here they are. Here are the 6 ways, and one of them is the pair of A and C. If the order does matter, then make sure that you're just consistent with that. Like if you're listing, oh, there's 12 total options, then you have to count A, C, and CA as 2 different options. So as long as you're consistent, you should still get a 6th here. You can't say the order matters sometimes and it doesn't matter other times. And like hopefully like seeing the list here where order matters and order doesn't matter. Yeah, what is the difficulty level of this problem? I mean, it's interesting because like, I don't think the probability necessarily, I mean, it's probability and it's quadratic. So, right, it's like 2 layers that are difficult. And when you put those 2 together, it's definitely a 700 plus level question. Cool, got it. Wow, we got to keep moving. We got to keep moving here. I hope we're all satisfied that the answer is E. I'm not sure how many other ways I could show it. Let's go on to the next one. All right, certain baseball player, 10% chance of hitting a home run in a single plate appearance. That's like this person is in the Hall of Fame or is not in the Hall of Fame because they used so many performance enhancing drugs that like that's how they get to this home run rate. But 10% home run rate is incredibly high. What's the probability that the player hits at least 1 home run over a span of 4 plate appearances? There's some trap answers in here. I will say answer B is a trap. Right, 2/5, 40% seems like it should be about right? 4 times 10% is 40%. This is like the expected value. That's like if this person goes to the plate 4 times, you'd expect them on average to hit 2/5 of a home run every 4 plate appearances. But that's not quite what this question's asking. Right, because sometimes in those 4 plate appearances, they'll hit 3 home runs or 2 home runs, and sometimes they'll hit none. Okay. A is a trap. Interesting. How is answer A a trap? I got someone telling me that answer A is a trap. Answer A is not right, so I also think it's a trap. Answer A is, yeah, 9 to the 4th. I should have exponent shortcuts on my keyboard, but answer A is 9 to the 4th, right? 3 to the 8th is 3 squared to the 4th, or 9 to the 4th, over 10 to the 4th. What is that in this problem? Chance of getting 0 home runs. Yeah, that's literally 9/10 times 9/10 times 9/10 times 9/10. And these are each probabilities that the baseball player will not hit a home run in a plate appearance. So like, what's the chance that, he does not hit a home run in this plate appearance, or she does not hit the home run? 90%, probably not gonna do it. There's a chance, a 10% chance, but most likely not gonna do it. Cool. What's the chance that the baseball player does not hit a home run in the first plate appearance and the second plate appearance? You multiply these. So what's the chance they don't hit a home run in any of the 4? Well, you have a 90% chance here, and a 90% chance here, and 90% chance here, and a 90% chance of missing on the 4th attempt. So that's the probability of never hitting the home run in these 4 plate appearances. We want to solve for the opposite of that, right? That they hit a home run, 1 or more. Okay. And so this is going to be one of those 1 minus problems. Yeah, I want chance of hitting none plus chance of hitting at least 1 equals 100%. So what we're doing here is we're figuring out the chance of hitting at least 1. The chance of hitting at least 1 is equal to 100%, or 1, minus the chance of hitting none. And guys, we just solved for the chance of hitting none. The chance of hitting none was A. This should be 1 minus, like throwing my dice everywhere, 1 minus 9 to the 4th over 10 to the 4th. Where is that answer? It is disguised. It is here. How about that? Yep, a difference of squares. I think question 1 was a difference of squares. I don't think question 3 is a difference of squares. I'll tell you that much here. Question 3 in the set. But this is it. This is the probability that it's about 34.5% that in 4 plate appearances they'll hit 1. What are some of these other ones? This is 36% because I don't know. I just created a chance that like maybe seems like you could get at. Does anyone know what answer E is? Answer E. I try to make answer choices that could be tempting if you solve them slightly incorrectly. Answer E is the chance that they hit exactly 1. That they hit exactly 1, and we can go ahead and just see how answer E. I'll just go ahead and put a star next to answer D right now so we know that it's correct. But how answer E is the chance of hitting exactly 1. Let's think about the ways you could hit exactly 1. We'll say a home run is a yes, and a no home run is a no, an N. So here are the ways to do it. You could, on your first plate appearance, home run, and then miss the other ones. You could hit a home run on your second only, on your third only, or on your fourth only. And these are the ways to do it. These are all ors. You could hit a home run with your first at bat and that's it, or you can hit a home run on your second plate appearance, or your third one, or only your fourth one. So what's the chance of hitting a home run on only your first plate appearance? Well, you'd have to do this. The chance of hitting a home run on your first plate appearance is 10%, 1 out of 10. And you'd have to miss here. And you'd have to miss here. And you'd have to miss on the last one. That is 9 to the 3rd over 10 to the 4th. And hopefully you can see that each of these outcomes is the same product. Like the 1/10 just kind of moves around in the order. So these would each be 9 to the 3rd over 10 to the 4th. You could do them any of those ways. You could do it this way, or this way, or this way, or this way. So you need to multiply this whole thing by 4. And that's answer E. Yeah, sum them up. And because there's 4, instead of summing the 4, I just multiply by 4, but that's it. Yeah. Cool, that one's pretty hard. I think that one's really hard. Actually, I think all of these problems are hard, but hopefully we're following on a little bit. And when you get the recording, you can pause and you can go back, and ideally it makes a little bit more sense on repeat viewing. Here's the last one. Have you guys ever seen that multiple choice problem? It's like very meta. It's like, what's the chance that you'll get this problem right? And answer A is 20% or 25%, and answer B is 50%, and answer C is 60%, and then answer E is 25% again, or answer D is 25% again. I think I've spent like an hour thinking about that problem, and at the end of it, I was like questioning what it means to be correct. Like, well, if you mean correct this way, I was getting very deep, and I don't have the philosophical training to do that. All right, we got 60 marbles in a bag. They're all mixed up. Joni's picking marbles. She's very diligent. She writes down the color, she puts the marbles back, and then she reshuffles them. So she's replacing the marble. So every time she picks a marble, there's a 1/3 chance of picking blue, a 1/3 chance of picking red, a 1/3 chance of picking yellow. All of that, all of like these first 4 lines are basically here to tell you that every time she picks a marble, there's a 1/3 chance she picks a certain color. And that's like how they can try to confuse you, right? We just need to rephrase that. We talk about rephrasing and data sufficiency. We just rephrase that in problem solving. Oh, every time she picks a marble, it's a 1/3 chance of being a certain color. Cool. She does it 5 times. What's the probability she wrote down red 3 or fewer times? What's the chance that she grabbed a red marble 3 or fewer times? Let's try to guess here. Let's think about like what guessing looks like. What do you think? Do you think the probability is like pretty high or pretty low that she grabbed red 3 or fewer times? I've got low, high, and higher. What's the probability that she grabs red 5 times? Like like she'd have to get, I don't know, is red good? Let's say red is good. She'd have to get pretty lucky to grab red 5 times, right? Yeah, she's like a 1 in 3 chance to get it the first time. And she has a 1 in 3 chance to get it the second time. And a 1 in 3 chance. So it's 1 in 3 to the 5th power. That's 1 out of 243, if you're wondering where all these 243s come from. That's pretty rare to go 5 for 5 on red marbles. So getting 5 is very hard, very rare. What about getting 4? What do you think about getting 4 red marbles? That like also seems pretty tough, right? Like each try is a 1 out of 3 chance. Like she could easily miss the first 2. Like go blue yellow or blue blue or yellow yellow. Like that's possible. She has no chance of getting 4 now, right? So I would say like getting 4 reds is still pretty rare. And so that means the rest are getting 3 reds or fewer. And so I would say getting 3 or fewer reds is pretty common. Like chances are that's what's going to happen. And that's what we're looking for. So what's the probability that she wrote down red? What does that mean, write down red? She just grabbed a red marble 3 or fewer times. Pretty high. This is likely. So I would be looking for an answer choice that's like pretty high here. And this is rare. This is still like less than 1/6. 40 out of 240 would be a 6. So it's just rarer than a 6th. 60 out of 240 would be a 4th. So this still seems rare. These are both over a half. And so I would just probably guess D or E here. And I think like if you don't want to do the math here, you can often kind of ballpark about like what you think a probability would be and take your pick. Now there's one other way that you might be able to guess here, and that is in probability questions. And we saw this on the previous one with the home run hitter, is to look for answer pairs, right? Like percentages, probabilities are classic problems that have answer pairs because we know that the total probabilities need to add to 1. So a lot of times 2 answer choices will be the evil twins of each other. They'll be the inverses, right? And so I don't see, do I see an inverse for this? Do I see anything that's 17/81? No, I don't. But I see that A and E are paired. And so I think you could guess answer E here and feel pretty good. All right, so the ways that she could pick red 3 or fewer times is to get red 3 times, get red 2 times, or get red 1 time, or get red 0 times. And those are going to be 4 pretty tough probabilities here, right? Like, think about like the ways you could get red 3 times. You could go red, 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 blue, yellow. You could go red, red, blue, yellow, red. You could go red, yellow, yellow, red, red. Red, blue, red, yellow, red. Like there's going to be so many ways to rearrange reds and yellows. Like that's only for getting red 3 times. You have to get red twice and get red once, get red nonce, 0 times. Okay. So I think the best way to do this is to figure out how you can get red all 5 times, how you can get red 4 of the 5 times, and then subtract it from 1. This is an extremely difficult problem, but this would be the way to do it, okay? We already said the chance of getting red 5 times, red and red and red and red and red is 1/3 to the 5th. Let's think about now. That's close, Jaydeep. That is very close. You need to do one other thing. But now we need to think about the ways that you could get red 4 times. So let's kind of sketch out what one of those ways looks like, right? It looks like this: red and red and red and red and not red, blue or yellow. I'll call it X. It just means like she lost. She didn't get the lucky red marbles. Yeah, JL, that looks good. Nice. Looks good. Great job. So what is the chance of this happening? Well, again, to get these first 4 red, you have to do 1/3 times 1/3 times 1/3. Come back. Times 1/3. That's how you get the first 4 reds. And now you have to not get red, because we're not going for 5 reds here. We're trying to get exactly 4 reds. Red, 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 and then not red. What is the chance of not getting red on the 5th pole? Joni's got a 2/3 chance to avoid the red marble. And so now what we'll do is say, well, that's one way she could have done it. Or she could have done it like this. Right? And the order does matter here. Like I'm being very specific. Like she could have done it this way, or she could have done it this way. All right. And that's going to be the exact same product, right? The 2/3 will just come as the 4th term. 1/3 times 1/3 times 1/3 times now 2/3, that the 4th one is a miss, times 1/3 here. So you can see what this is going to be. This is going to be 2/3 to the 5th. And so will this one. 2/3 to the 5th. And so will this one. I'm not gonna put spaces in here. And so will this one. And so will this one. These will all be 2/3 to the 5th. So you will have 5 times 2/3 to the 5th. Plus this one. And so that's 5 times 2/3 to the 5th is 10/3 to the 5th. This is 1/3 to the 5th. That the odds of getting 5 or 4 is 11/3 to the 5th. And so the odds of avoiding that, of getting 3 or fewer, is 1 minus 11/243, or 232/243. Super hard problem. But hopefully, like we can kind of see those basic mechanics of number of outcomes, right? Number of desired outcomes over number of total outcomes. Or we can remember that when we multiply, when we need multiple things to happen to get to our result, we multiply. And we have multiple options for getting to our result, right? Or this, or you could do it this way, or you could do it this way, or you could do it this way. We add those probability pathways. That's it. Of course, you can also guess here, have a pretty good case at guessing D or E and saying, well, most of the time she's not going to get 5 or 4 reds because it's hard to do that. And then look for answer pairs. I think you could be in good shape here, and even on the previous problem. Woo, cool. That was hard. Those are those are some hard ones. Yeah, I would encourage you, if you're watching on the video, on the recording, to just kind of like maybe let some of this sit in for a little bit, and then go back and try some of these problems again. And just remember, like, you guys can get 49s and 50s. You can get 49s and 50s on this exam, avoiding problems like all the ones that were in this set. Yeah, like you could, I mean, first of all, you're not going to get, the probability that you get 3 probability questions on your quant section is very low. I'll just say that. But yeah, if you see one of these on your exam, I wouldn't feel bad missing it or skipping it, or both. Yeah, plus remember, the probability that you randomly guess it correctly is 20%. That's nothing to sneeze at. That's nothing to sneeze at. Cool. All right. Do I want to be nice? Sure, I'll be nice. I'll go over a little bit because, you know, I like this stuff. I'm a huge dork when it comes to these problems. And yeah, Gina, thanks. We'll do the bonus problem. I did say I have one, and so I'll give you a sneak peek at one of our books. This problem is presented by our advanced quant book. I'll give you some time to think through it, and then we'll talk. Yeah, if you have to run, totally get it. We advertise this as being a free prep hour, not free prep 71 minutes. So if you got to run, that's cool. JD, was that one of our exams, on the Manhattan exam, or is that on an official exam? Probably one of ours, because you don't know the difficulty on the real ones. What do I want to say about that? I'll say, trying to think about how to say this. I'll just say this, and I don't mind saying this on the recording either. I think our exams are hard, and one of the things that I think makes our exams tough is they really try to train you to showcase better time management. And so if you are having to rush through a bunch of problems at the end and you miss a bunch of them, if you miss them all, that shows that you're not demonstrating good time management, and so you're like getting kind of punished there. I also think that, like, if you miss a string of problems in a row on the real thing, you also kind of get dinged. I don't know if you get dinged as severely as you do on our exams, but what I would say here, JD, is like the moral of the story is you just don't want to be in a position where you have to guess on that many problems at the end, on the Manhattan exams or on the real thing, we need to miss questions earlier, because likely what's going to happen is if you miss 7 questions in a row, like by the time you miss like 4 questions in a row, the algorithm's going to adjust a little bit and then start feeding you maybe some slightly easier ones, and then you're going to miss those too. On our algorithm, it's going to be based on like your current. Ours reacts a little bit differently than the real thing, and that's pretty much what I can say to that. Yeah. Moral of the story is you just don't want to be in that position. Cool, guys. All right. Hopefully you've had time to read this down. If you're watching on video and you're distracted by me like blabbing through that, go ahead and just pause it here, but we're going to go talk through it. There's this quadratic that's set equal to Q. P could be any positive integer between 1 and 10. Ashley, that looks pretty good to me. I think. No, try that again. Sorry. Trying to remember what the answer is on this problem, and I couldn't quite remember. I guess we'll find out what it is in a second. P could be any positive integer between 1 and 10. What's the probability that Q is less than 0? I think this is going to take too long to plug them in. Like, well, what if P is 1? Like, what happens here? Oh, plus 4. That's not going to work. P can't be 1. What if P is 2? 4 minus 26, 20. That's going to be 2. That's going to take really long. All right. Thanks, Vishnu. Thanks for hanging out. Appreciate it. So what I want to do here is say, look, whenever you see a quadratic, let's see if we can factor it. All right. Let's see if we can factor this quadratic. and this quadratic is factorable. Yes, Ashley, those are the roots, but we need to think about how those roots work here a little bit. So this should factor into p minus 8 and p minus 5 equals q. Of course, we're trying to find out when this is less than 0. So what we want to say is like p minus 8, p minus 5 is equal to something less than 0. So I'm going to put that here. When is p minus 8 times p minus 5 less than 0? Well, this is a product. Guys, when is a product less than 0? Yes, Sid, that looks good. When they have opposite signs, that's right. So when these have opposite signs. Now, we need to think about how these can have opposite signs, right? It's not the case that like one of them could be positive and one of them could be negative. It doesn't matter which one's which, because p minus 8 is always less than p minus 5, right? P minus 8 is literally 3 lower than p minus 5. So the only chance we've got here is for when p minus 8 is negative and p plus 5 is positive, right? We need this product to be negative. So one has to be negative, one has to be positive. And it has to be in this order because p minus 8 must be less than p minus 5. So I need p minus 8 to be less than 0, right? It has to be negative. And I need p minus 5 to be positive or greater than 0. So I need p to be less than 8, and I need p to be greater than 5, which means I need p to be between 5 and 8. So the only way this can happen is if p is 6 or p is 7. There is a 1/10 chance that p is 6 if it's chosen between 1 and 10. And there is a 1/10 chance that p is 7, or that we select 7 when we choose it from between 1 and 10. A 10th plus a 10th is 2/10 or 1/5. This one is answer B. Yes, a 5th is the answer. Good stuff. Guys, this is from our advanced quant book, which is filled with more questions, kind of like the questions in the set we just did. It's a good resource if you are in the upper 40s in quant and trying to go climb those extra few points, I think. Awesome stuff here, guys. Thanks for being very responsive in chat today. It was really, really great. One of the better sessions with that. And I hope to see you at one of these again. I'm going to be doing one of these, I guess, in the middle of October, October 18th, I think I said. Hope to see you there. Thanks, guys. I'll stick around for a sec if you have a few questions. Otherwise, I'll see you a little bit later. I think I'm going to go ahead and stop the recording here, though. Thanks, YouTube.